We have the recording going, we have the slides shared, so we're good to go. Okay, so today we are going to discuss a kind of a controversial topic, whether we figured out DevOps or not, and if we did, what's next. So my name is Baruch Sadogurski. I'm at J Baruch everywhere, developer productivity advocate and developer relations advisor with a company called Gradle that you might know by their build tool, the most popular build tool in the JVM ecosystem called Gradle, and maybe by the tool called Gradle Velocity, which we're going to mention a little bit today. I started as a developer, particularly Java developer, many years ago, and then switched to DevOps with another company called JFrog that you might heard as well, and now doing developer productivity engineering that we're going to talk about today as well. So I co-authored a couple of books, DevOps Tools for Java Developers, which is very relevant for this connection between developers and DevOps and everything in between, and the Liquid Software, kind of a visionary book about how to release software properly. The most important slide of this talk is this one. If you go to speaking.jbaruch, you can go there even right now, you'll find a page dedicated to this webinar. It already has the slides uploaded. I'll upload the video that I record right now just after it will be rendered by Zoom, and all the links to everything that we're going to speak about, including the books that I just mentioned and everything else, is going to be there in this page throughout our presentation. The link is on the bottom of every slide, so you will know where to go, together with my handle at jbaruch everywhere, as I mentioned, a hashtag DPE for developer productivity engineering, and hashtag DevOps Vision. A couple of words about DevOps Vision. It's the conference that is coming up in December. DevOps conference, obviously co-located with MLOps conference. So if you are looking at this very exciting and emerging industry, that might be a good conference for you as well. In the end of this talk, I will have a very nice discount to share with you to DevOps Vision. As I mentioned, it's in December in Florida, in a beautiful resort on the beach. There are so many reasons to attend and not a single one not to. Stay tuned. I will share a very nice discount with you as well in the end of this talk. So yeah, hashtag DevOps Vision, another one that you want to mention maybe when you talk about this talk online. So yeah, I think an interesting way to look at where we stand in our adoption of DevOps is to look at the decade of DORA reports. DORA stands for I don't remember, something, an assessment, research and assessment. DevOps, research and assessment. Here we go. DevOps, sorry. Yeah. DevOps Research and Assessment organization, and they publish for 10 years. You can see here in the bottom, 10 years of DORA, a report about state of DevOps. It has a long history. It started as State of DevOps report published by a company named Puppet that DevOps veterans of you might remember. And then it became like thing of itself in the organization called DORA and Accelerate. And then now it's under the umbrella of Google Cloud. DORA report assess DevOps at 4 main characteristics, or four main functions. Deployment frequency, how fast an organization is capable of deploying. Change lead time, how long changes take to get deployed, change failure rate, how many of those deployments are unsuccessful, and mean time to recovery. When a deployment is unsuccessful, how long it takes to fix it. So this is how it is described. Change lead time, the time it takes for a code commit or change to be successfully deployed in production, deployment frequency, how often application changes are deployed to production, change failure rate, the percentage of deployments that cause failures in production or require hotfix or bottlenecks, and failed deployment recovery time, the time that it takes to recover from a failed deployment, right? And let's go through the years for the entire 10 years and see how the industry deals with those metrics. So here is the first DORA report, Puppet DORA report 2015. And you can see here the distribution in figures 2, 3, and 4 between back in there, it was only 3 factors: deployment frequency, deployment lead time, and mean time to recover from failed deployment. And you can see that the columns in each of every one of them, super high, high, medium, low, are the performers groups, right? So there are those that perform super great, those that perform high, those that perform medium, and those that perform low. And you can see that's not a very good way to represent it. They switch to another one. We're going to summarize it very soon, so we don't need to look at this particular one. So this is how it looked at the Accelerate DORA report in 2018. And you can see here that there are the same 4 groups: elite, high, medium, and low. And here you can already see their results in a more convenient way, I would say, right? So deployment frequency for elite, for example, is multiple times a day, comparing to, for example, for low, between once per week and once per month deployment frequency. And for example, change failure rate, how frequent a deployment fails when deploying to production, between up to 15% with elite and 46 to 60, about half of the deployments are bad for the low performance, right? And then you can see I took the last year, 2024, that would be your Google Cloud DORA report, and you can see here that the elite still lead time is or deployment frequency is multiple on-demand, multiple deployments a day. And you can see that change fail rate is still 0 to 5%, and for a low, between 1 month and 6 months, or and then the fail rate has actually went down a little bit from what it was, 46 to 60 to 40%. It's interesting to see how the percentage of respondents also changed, how many of those are elite and high performance, medium performance, and low. So if we look at 2018, for example, 7% are elite. If we look at 24, 19% are elite. So that's more than double. And then high performance are 48%, because here the elite was a part of it. So if we extract elite to be a group of their own, so we will say 7% elite, 41% high performers. In 24, it will be 20% elite and then 22% high performers. So together, it's like 43%, which is a little bit less than it used to be in 2018, which is interesting, right? And then you can see high 22 used to be high with it, sorry. Medium 35 used to be 37, and then low 25 used to be 15. That's interesting. A lot of organizations slided into low performers over the last 6 years, but you need to remember that that's because the requirements, even for low performance, got higher. For example, the change fail rate that we looked and went down from 60% to 40%. So whoever is now deploys 40 with 40% success, and used to be medium performers, now are considered low performance. So we can see here the cluster changes over time from 2018, when the first the cluster size was reported, to 24, and you can see that they are kind of remained more or less the same, with some changes between the medium performance, where went up in 2021, but now kind of being eaten a little bit by the low performers. And again, that's because what considered medium in 2021 now consider low. So there's not a lot of change. Which brings me to this hot take. We figured DevOps out. Why would I claim that looking on this graph? Well, because there are no significant changes. You can see how the significant changes kind of ended up, the rise and the success kind of ended up somewhere in 2021. And it's stagnation since there. And that's because whoever wanted to do DevOps correctly managed to do that in the whatever 10 years that passed for DevOps since its inception to 2021. 10 years is a lot of a time for methodology to mature, and DevOps matured, and now we know exactly how to do it. Do we still have low performers? Of course, but that's not because they don't know how to do it. That's because different reasons. For example, they might not have the organizational will to implement DevOps. They might not have the right personnel to go ahead with it. There might be multiple reasons why people cannot approach implementing DevOps. But whoever approaches implementing DevOps knows exactly what to do and how to do it. There are tons of material, there are tons of certifications and courses and training and advisory and consultants, and really people know what to do. And what we saw, this graph illustrates this very well. People really excel at DevOps if they want to. So for me, that means that DevOps is figured out. We know how to do DevOps. We might not do it. A lot of the industry might not do it. Half of the industry might not do it. But it still doesn't mean that we don't know what to do or how to do it. It just means that some organizations embarked on this journey, embarked on it with the seriousness that it requires, and succeeded, and the others didn't. And this is completely fine. There are organizations that still do waterfall in 2024, and it's not because we don't know how to do agile. It's because this is their deliberate decision on how they want to proceed. And it's exactly the same with DevOps. Whoever wants to do DevOps knows how to do DevOps. So yeah, I do consider it figured out. Now let's look a little bit more on those trends. So what I did here is I plotted the results of the different groups with their particular metrics over time. So you can see here how the low performers got better with failure rate, and got better with like other metrics, but also got worse with some of them. So for example, you can see that lead time kind of plummeted between 2018 and 2021, then got a little bit better. Well, low performers are generally low. Medium performers, same thing, right? So they got better in 2018 to 2021. Remember that the plummeting in 2021 is also because the sizes, the cohorts shifted, right? Remember how who used to be medium kind of became low. So this is why you see the dip here, because they used to be in another group, and they are still not good. So they dragged the medium performance down a little bit in 2021. Now, this is very interesting. You can see here for high performers how they actually got worse in failure rate for a little bit. And the most fascinating for me is this graph. Now, elite performers were also always the group of their own that didn't change much. And you can see, for example, how they are doing best across the almost across the board with recovery time and deployment frequency. Since 2014, the deployment frequency for the elite group was always on demand. When they wanted to release software, they went ahead and released it. And failure rate actually improved. They had some failure rate and now they are better. But the most fascinating here is the decrease in lead time. Now, decrease in lead time for elite performers is particularly interesting because it is not about DevOps. Let's talk about it for a second. How did we used to describe DevOps back 10 years ago, 15 years ago? It was a very naive description of like, hey, this is something between DevOps and QA. So DevOps, that's the name. And then we kind of, hey, by the way, quality is also important. So this is how we showed it somewhere between DevOps and QA. But what between DevOps and QA? We spoke about, hey, maybe it's someone who does all of that as their DevOps engineer, but then we kind of realized that DevOps engineer is not even a thing, right? Instead, it's something that has to do with changes with people, process, and tools. So when we change how the people work in terms of processes and then provide them with different set of tools that they used to have, then maybe DevOps happens. And basically, the key was about how to make productive people iterate on productive process by using productive tools to be able to excel in software delivery. So this is, I would say, the most complete definition of DevOps, right? It's a collaborative process around that people do and work with tools to get something done together, right? And we know exactly now, as I mentioned, we figured out DevOps, we know exactly most of the things. So we know what productive teams are. Productive teams are the product teams or feature teams or empowered teams, or call them whatever you like, where you have representatives from every discipline. It's where developers work together with ops people to build those pipelines and then release software on those pipelines. And then we have the quality people contributing to those pipelines by introducing quality checks into them. So when we release software, the failure rate will go down and not up by adding more and more automatic checks. And then we bring in security people who also add security gates to those pipelines. So we will make sure that the code is secure and what's not. And then product people are in those teams and guide what needs to be done, derived by feedback from the users and all this kind of stuff. So basically, we know what productive team is. It's the opposite of silo. It's where people sit together and develop together what they need to do. Productive tools, well, also kind of sorta. I mean, a lot of YAML, which is not exactly productive, but jokes aside, generally we know now how to tackle server-side, particularly server-side development in a way that it's very, very scalable and very, very very, very resilient. The entire concept that we treat hardware as it was software, configuration is code, infrastructure is code, cattle over pets, and all these kind of concepts that make the the environments very easy to deploy to, very easy to roll back, very scalable, very robust, very resilient. We know how to do that. We figured that out as well. But what about productive people, and how do we make people more productive? And here I would say that since we figured everything else out, the production system of our production systems, and that will be your development environments, is what is our next frontier. And this exactly fits into what we saw from the data of decline in lead time for elite teams. Why? Because software becomes more and more complicated, and lead time is about a lead. It's something that a time from the inception of the idea to the time that it hits our excellent DevOps production systems. This is about development efficiency. This is about development productivity. This is about the production, the effectiveness and the productivity of our production systems. And this is a real pain. For example, when your builds and tests are slow, this obviously hurts your lead time, even if your production environment is excellent and top-notch and what's not. And the other problems, like inability to troubleshoot and determine the root cause of a build, obviously slows down your lead time. Insufficient observability of analytics on a build trends slows down your build time, so your lead time. So those concepts that are very tied to first productive people, developer productivity, and the production systems of your production systems, your development environment, it all comes together to hurt this one aspect that is actually still not figured out in the entirety of the DORA metrics, and that's the lead time. And this is why it's declining. So the solution here is developer productivity. And there are a lot of approaches on how can we achieve this developer productivity. And obviously developer productivity is all the rage now, and you heard about it a lot. And this is another, I would say, way to look at it through engineering lenses. So developer productivity engineering is how can we engineer improvement in developer productivity. There are many approaches to that. AI and LLMs is one of them, and well-being and avoidance of burnout is another, and all of them are important. All of them play together to, in the end of the day, create this productivity. But developer productivity engineering focuses on the engineering aspect of developer productivity, right? And here are some ways to do it. For example, one of the most important ones is foster faster feedback. Faster feedback loops, less context switching is absolutely critical for improving the lead time of our DevOps posture. Actively elimination of friction and toil allowed focus and better productivity, eventually better lead times. Collaborate through tools and platforms that promote transparency and sharing understanding. Prioritization of automation and eliminating bottlenecks. We already did it for our production environments. Now it's time to automate manual tasks and focus on bottlenecks in our development environments as well. Rigorous observability. Again, we did it perfectly for our production environment. It's time to do it for our development environment as well. Team treat development environments as production and maintain observability to create the better developer experience and developer productivity. cultivate the mindset of developer productivity and developer experience. And we have a lot of output, but we need to concentrate on meaningful outcomes and resist the noise that we have. Again, we do it very well with production environments just because we had to. But now it's time to take those lessons into our development environments as well. Let's talk about concrete examples of developer productivity engineering and how we can improve our lead times using that. So small improvements in developer productivity engineering can make a huge difference. For example, letting developers use IDE that they are productive with. There are people who are most productive with Vim. There are people who are more productive with IntelliJ or VS Code. Stuff like, hey, everybody should use Eclipse when no one actually likes it or productive in it is actually counterproductive. It slows down your velocity as a developer, eventually as a team, eventually as a product, and obviously it hurts the lead time that we spoke about. Stuff like testing. How can we test more efficiently without waiting for days on end for some very expensive, cumbersome, and buggy testing environment to be available for us? Well, stuff like test containers excel in making integration tests almost as easy, cheap, and fast as unit tests, and obviously improves our lead time. Better code quality. This is not only build time, but also failure rate. In the end of the day, if we can find bugs before we even go to production, this improves failure rate as well. Tools like Sonar can be really, really good at that. Going back to testing more reliably, and generally avoiding breaking builds that shouldn't be broken by detecting flaky tests and fighting them. And foster faster feedback. Let's talk about foster faster feedback. So to understand how we can improve feedback, let's talk about what feedback do we actually expect comparing to what feedback do we actually see, right? So for example, when we write code in our IDE, we expect sub-seconds efficiency. We write the code, it marks red if we made a typo and typed spring instead of string or vice versa. Build, we expect it to be very, very fast because we're waiting for it to see the results of what we just did. CI, this is also about the results of what we just did, but this we expect it to be slower because it's integration. It might run more tests. It might run the tests together with work that other people did, and we generally don't wait for it, so we're okay for it to be faster. And then production. This is also very important feedback for us, whether our software works or not. But we also know that it will be hours or days until our change will hit production. So we obviously don't sit and wait for it without doing anything else. So basically, the farther we are from developers, the longer expected feedback is, which is, or to put it the other way, when we shift left, we expect faster feedback, which is absolutely natural and makes a lot of sense. And this is also what we usually see with an exception of a build. Now, yes, CI is minutes or hours. Yes, production is hours or days. Yes, IDE is really sub-second feedback. Build is usually longer than we want it to be. And, you know, the ultimate proof that build is longer than we want it to be is that there is an XCD comics about it. And you probably saw this one. This is one of their more famous ones. And it's funny first time you look at it, but then when you actually start thinking about it, suddenly it's not that great. It's not that great because yes, it might be fun to slack a little bit when your build is slow for the first time, but when your build is always slow and you're always distracted, this is actually not something fun. It's much more like this. You're getting really upset that your build is slow. And not only that, there is not much you personally can do about it on the surface, because build is a very complicated concept that is usually will be outside of the expertise of like your average developer. Bruce Eckel uh, put it great in his critical article about Gradle, when he said, to do anything, you have to know everything. Now, while Bruce particularly referred to Gradle as someone who dealt a lot with any possible package manager in the industry on my days with JFrog, I can attest this is true for every build tool, dependency manager, or package manager out there. They're all very complicated just because it's a complicated domain. And this domain is not the same as your application software development. So as a developer, if you are not deeply into it, not only it is slow that annoys you, you also have no idea why. And if you unpack it and look at what is build, it's project setup, downloading the dependencies, and then generating artifacts, and then testing those artifacts and deploying those artifacts to the cloud. What can go wrong is basically everything. It can be project setup, that downloading the internet, generating artifacts, tests, artifact deployment. Anything can go wrong at any time. And this is really frustrating for developers. So the build is frustrating the developers, and slow build in particular. And what do we do in order to fix something that we not really understand what's going on? Well, we ask our LLMs. So I went and asked ChatGPT on what are the techniques can I use to speed up Maven build. And the first recommendation was skip tests. Now, this is really, really wrong. It's really wrong because the reason we run our local build is to get feedback on what we've done. And tests are exactly what this feedback comes out of, right? This is kind of the first thing that why are we doing the build is to run the test. And you know what? If we are willing to give up on this kind of feedback, how about we skip compilation as well? Our test is going to be much faster, no doubt about it. Our build is going to be much faster. And you know what? It will compile on the CI for the first time. How about that? And it obviously doesn't make any sense because we want faster feedback, not less feedback. We want our build to run our tests, but we wanted to run it fast. So yeah, so I mentioned we definitely want our feedback on our compilation, whether our code compiles, and we want our feedback on the tests to check that it actually does what we expect it to do. What else? What else can we want as a feedback? We can look at the pipelines that we spoke about, the quality gates that we do there as a part of our DevOps and excellence. And as I mentioned, we know exactly what to do in order to get inspiration for what feedback do we want. So what a perfect CI/CD quality pipeline quality gates look like. So there are basic stuff like, well, it compiles, right? And the unit tests pass and the integration tests pass. And then there are deeper quality analysis, for example, code coverage. Did we actually test enough? And linting is the code is in the right standard. And then static code analysis for quality, stuff like Sonar that we spoke about. And then security gates like dependency scanning and secret scanning. Did we push, do we have like some secrets in our code that shouldn't be there? And static security code analysis to find stuff like hey, there is an opportunity for SQL injection here that need to be fixed and this kind of stuff. So non-functional requirements like load testing and resource utilization and compliance, right? So this is very robust set of feedback gathering quality gates. This is actually what stands between us and low failure rates in production. We check all that, and then we can say, okay, we are confident that we will get whatever under 15% failure rate, the elite, the gold standard for the low failure rate that we want in our production, or was it 5? Whatever, like very low percentage of failure rate. How do we guarantee it? With having all this feedback. Now, this feedback is in our CI pipeline, which is great, which is excellent, but it's not really good for our immediate feedback, because our immediate feedback is in the local build time and not in the CI. CI, to remind you, is not immediate. There are generally two types of feedback, asynchronous and synchronous, and CI is the asynchronous type of feedback. We don't wait for it. It takes a long time, so we do something else. But then the results will be very distracting if we need to get back and fix whatever is broken in CI. So basically, if we only rely on CI as our first feedback, it will be very distracting because we won't be able to trust our software until we get this feedback. I had a very good episode about it with Josh Long from the Sprint Framework in his last beautiful podcast episode, one of the last. I'll add a link to the show notes. I didn't think about it at the time, but it's actually a very good resource to see how a really excellent developer talks about it. And what Josh told me is like, hey, Baruch, you know what? I cannot do what you suggest here to do, and that's not waiting for CI, it's just doing something else. When I committed something to CI pipeline, it's kind of hard for me to concentrate on other stuff because I'm thinking about, will it pass? Will it fail? If it fails, I need to go back and fix it. So the old context of what I used to do is still on my mind, and it distracts me from doing something else. And this is a perfect description of not enough synchronous feedback, right? So if the build, which is synchronous feedback, doesn't give Josh enough confidence that his code will probably be fine in CI, he really cannot concentrate on the new stuff. This is very profound. So what we want is a very robust feedback on the build, because when we have it, we can say, okay, I'm pretty sure that CI is going to be fine because local build is fine. For that, we need a lot of feedback in the local build, but it also has to be fast, because if my local build is slow, I will treat it as CI. I will start doing something else, but then I cannot really concentrate on something else because my local build is running, but I also cannot wait and sit and wait for local build because it's too long. So this is an annoying problem that we have this commit line as the line between synchronous and asynchronous, and then we have really good feedback on the asynchronous side, but we really need it on the synchronous side. So we want our build to be almost as complete in terms of amount of feedback as our CI, but then we naturally think that it will slow the build down. So this is kind of choose one, but we actually want to choose both. We want as much feedback as possible in the synchronous part of the build, but we also want it fast because it's the synchronous part of the build. We're waiting for it. We need it to be fast. So how can we do it? How can we get more feedback and keep it fast? There are two main techniques. The first is avoidance. Basically, avoidance means that we will skip everything that can be skipped during the build, but obviously no more because we need the feedback, right? So first, something that all the modern build tools do and do very well is incremental build. Whenever you run your Gradle build or Maven build or whatever build, it will skip some parts that it thinks that are safe to be skipped. Something that you didn't touch, something that you already built, something that is in the module that shouldn't be affected by whatever you changed, this kind of stuff. The problem with incremental build that it's not perfect. First, it knows that something is up to date and doesn't need to be built based on produced artifact. It will look at, if we're talking about Java, at your jar file, at your class files and say, okay, this is already been built, so I don't need to build it again. The problem is that there, first of all, those files might be deleted if I run a clean build, for example, or it's also limited to only tasks that produce artifacts. If I have some work in my build that didn't end up producing artifacts, this cannot be up to date with incremental build, which is very annoying. The other problem with incremental builds is that they actually rely on architectural decisions of your project. Your project needs to be structured in a certain way with modules dependent on each other, so the build can make those decisions of what needs to be tested based on what changed. Sometimes those decisions cannot be made or just weren't made, and now we're stuck with the build running parts that we need or that we don't need, or skipping parts that we do need just because our build structure is not exactly as our build tool expects it. There is a better way, it's actually a complementary way, which is build caching. Now, build caching makes the build faster, exactly like incremental build, but not only it makes it for your build, it also makes it for everybody in your team by sharing the cache. You can say, okay, I built this module, and now instead of you building it, you didn't touch it, but there are changes which are from me, just take my cache and then skip building because I already did that. It makes the build faster always because it doesn't rely on the produced artifacts. It will generate cache results that are not the same as artifacts, and it also makes all the parts of the build faster because the cache can be achieved not only for tasks that generate artifacts, but actually for any task. And that's obviously much bigger impact on the build, including configuration stage and other kind of stuff. So here I have an example of a build that you can see here took 20 serial execution, took 15 minutes. Now it took 15 minutes after huge avoidance savings, 40 minutes, right? So it should have take almost an hour, 55 minutes, but it took only 15 because of the avoidance settings. And you can see that the up-to-date part, which is the incremental build, only provided half of those avoidance of those avoidance savings. The other half was provided by a combination of a local and a remote build cache that actually saved even more. It saved like 25 seconds comparing to 20 of the standard incremental build. So you can see how when working together, those avoidance techniques of incremental build and caching save so much and allow you to avoid a lot of the build work that doesn't have to be. Now, I would say that 15 minutes is still a lot, but it's definitely better than 55. Another very powerful technique is predictive test selection. Now, as I mentioned, incremental build already tries to avoid testing what doesn't need to be tested. But the way it approaches is through architectural decisions on your project. So it will try to guess how modules are dependent to each other and which module should be affected by whatever you build and which shouldn't. But there is a better way, and that's the predictive test selection. Predictive test selection, instead of trying to guess what your architectural decisions are, just observes your project being built and tested over and over again. And after a certain period of time that it observes it, it starts making conclusions of what changes actually fail what tests. And then it can start skipping tests with a high degree of confidence, guessing which changes will not ever or probably fail tests, and then just skip those tests entirely. So code changes and test results are thrown into the learning model. Learning model observes your build. Those are the code changes. We run all the tests. Some of them pass, some of them fail. Over time, it learns that which changes fail which tests. If some changes never fail certain tests, those tests we don't need to run because we're pretty sure they will be fine. Right? The project model predicts which changes fail which tests, and then we can skip them. So basically, what changes and what changed and where it is changed is being learned, and then it is correlate with the observed test failures, and then it predicts which changes will fail which tests, and then obviously we can skip the tests that are likely not to fail, right? And watching this model learn is fascinating because it comes to human level conclusions without understanding the reasoning behind it, right? So here is an example. A model learn that the more tests a project has, the less they break. For us as humans, this makes perfect sense because we know that it's a part of the hygiene of test coverage that provides this test quality that guarantees that the more tests we have, the less they fail. And then refactoring in Java, that's another conclusion, absolutely fascinating, that refactoring in Java break tests less than in JavaScript. So for us, it's like, obviously, Java is a statically compiled language, so it has much more reliable refactoring options in JavaScript. But the model doesn't know anything about it. It doesn't know what Java is. It doesn't know what JavaScript is. It doesn't know what statically typed language means. All it knows that given changes in files that has .java extension and compare them with the changes in the files with the .js extension, the former fail much less in the test than the latter. Without understanding why, it came to a completely reasonable outcome that for us is obviously absolutely natural, right? So you can see here, Spring Framework, talk a lot about Spring today, that we mentioned Josh earlier. So Spring Framework runs predictive test selection in simulation mode, in learning mode. It means that we can see how effective the model is, and you can see here that the model predicts failures in 98.7% confidence. So it makes mistakes, but so rarely that we can safely disregard it for our local build. We still want to run all the tests in CI, but that's okay. We don't wait for CI. We don't care how long it is. But for a local build, we can skip all those tests. And you can see how over the last 3 years, the Spring team could save 61 days of serial build if they were enable this predictive test selection running in production. In Gradle, we grateful for them to keep running it in simulation, because only in simulation we can actually see the real results, because it compares what it guessed to what actually happens. If we run it in production, there is no, that we only have one side that it's guessing and whether it's correct or not. So in any way, very precise model. We can skip tons of time in our local build. Now, what cannot be skipped still needs to be done. There is work to be done. We changed some code. We need to build it. We need to test it. We need to check what's going on. This part, we need to speed up as much as possible. And the one most significant trick to speed up your build is using your power of your entire machine to parallelize your tests. So this is also the reason why your boss should buy you the bleeding edge machine, whatever M4 Pro Max is out today. I have a project running on this machine that I have here, which is a relatively old M2, I think, from a couple of years ago. And you can see that this test, that the build that I have it's 2 minutes and change. And most of those 2 minutes, 1 minute, 59 seconds is the test phase, which obviously makes sense. And it's the same for all of you. Now, with one line of code, I improve this build 12 times. I make it 12 times faster. And this line of code is use all the available processors. Boom, 12 times faster with one line of code in Gradle build tool, completely free, available for each and every one of you today. You know what has more power than my machine? The cloud. CI uses what's used fan-out techniques to speed up tests in CI and run them in parallel, which is nice, but it's really not that critical, because CI is not, we don't wait for CI, right? It's not synchronous, it's asynchronous. We don't care how long CI takes. Well, up to a point. But we want to use the same technique for where it really matters in our local build, which we wait for because it's a synchronous feedback. So we need to enjoy it for local builds. We can use the cloud to distribute test load for our local build. We have a build that runs on our machine for tests. It will reach to the cloud, run the test out there, collect them back, and continue with the local build, improving, obviously, the time. And then we can run all the needed tests that we need to run without skipping, as ChatGPT suggested for me to do in Maven. Right? And the CI fan-out technique is nice, but it's not perfect because it relies on CI infrastructure. And CI infrastructure isn't optimized for speed because it's not real-time feedback. It's not synchronous feedback. It doesn't care. So the agents probably are not as fast as they can be. If we do it for local build and we optimize it for performance and for real-time feedback, it will speed up our local builds dramatically. And then obviously we need to watch for degradations, right? Measure local build times across times and environments, detect those trends, find root causes, and improve. And basically, when we see this, and this is your boiling the frog situation, when the build becomes slower and slower over time, we need to be able to see it and then fight it and then improve our development experience. And the lead time, the same DevOps lead time that we started speaking about in the beginning. And again, on Unreal, you can see that 84% of organizations that are actually starting doing that report dramatic improvements. And I guess the same 84% report developer joy, which is excellent by itself. So developer productivity is the next frontier. We figured out most of DevOps with this slight exception of the lead time. And then the idea is that if you want to excel in your production environment, you know exactly how. But what about your path to production, the work there to be done? And developer productivity engineering is definitely the way to go. So what you can learn more today and start doing, you can start with Gradle and Maven Speed Challenge. That's a speed challenge that Gradle runs, and it works only also with Maven, that allows you to implement those small changes that we spoke about in our presentation, and also win some prizes on the way. You can be the DPE agent of change in your organization and say, okay, this is what we need to focus next. DP handbook will have a book that explains what we just spoke about and more. And you know where to find the link, speaking.jbaruch, or scan this QR code, it takes you to the same place. And you can watch the DP Summit keynotes, which are out there from the DPE conference, annual DPE conference that happened in San Francisco in September. And now, as I promised to you, the next conference that you are going to attend, DevOps Vision, Clearwater, Florida in December. Excellent location, excellent timing. Where do you want to be in the beginning of December in Northern Florida? And $500 off early bird pricing, which is a discount on top of discount if you use the code DV5BAR-W. I don't know what W stands for. Everything else is pretty self-explanatory. DevOps Vision 500 Baruch. So use that and get your discount today. And I will be delighted to see you all in December in Florida. And with that, we are on the top of the hour, but if you have some questions, I will be happy to stay around for another 5-10 minutes taking any questions. Thank you very much. You can type them in, or you can raise your hand and I will be happy to unmute you. All right, I guess there are no questions. Thank you very much for joining, and I'll see you, as I mentioned, Clearwater, Florida in December. Thank you and bye-bye.